Perfect. So, hi guys. So in previous video, we derived the Han window, and in Han window, we saw the plot of the Han window itself, and the plot itself somewhat looks like, mm, yeah, this is the plot. So we saw the Han window over here, and uh, this was the plot for Han window. And we discussed why we are windowing the signal, and when we plot it, so it took three wins instead of one win. And this in blue represents the sinusoidal when we have rectangular window, but when we have Hahn window, the main lobe uh, occupies three bins. So what happens in Han window is basically we are tapering off the unwanted impulse or unwanted spike due to periodicity. So this spike, which is causing FFT leakage, so we taper it off by a smooth window, and we say that the beginning and the ends of this window is being tapered off. That's how we wait for the main data, which we are okay with, but the impulse which we are not okay with in the ends are being tapered out. So basically it's just like realizing we have our signal with M samples, and we are using a Hahn window, which is represented by this um, value. And then we also have a rectangular window along with it. And then when we plot it, so we came across the condition where we saw that it took three bins, where we saw that the magnitude of the peak of a coefficient of A is basically half of the input signal, and for the left one and right one, which is A plus minus 2 pi by n, it'll give amplitude of 1/4 of the input. So basically we have to note that there is different amplitudes relation between the main bin and the two side peaks or the two side bins. So the main bin corresponding to A is having let's say half of the input amplitude, and other ones are having 1/4 of the input amplitude. So when we see the plot, so the plot, this bin and this bin basically is represented like this. And as we said that it is contributing half of the input amplitude, right? So the drop is, so basically this is the Hahn window, and for this is our squared window. So this is our square window. So the difference is basically 6 dB. Why? Because it's just half the amplitude. And when it corresponds to this thing, so again, this is 1/4. So basically, this difference is also 6 dB. So over here, we can see from this point to this point, the drop is 12 dB. And from the main bin to the rectangular bin, I mean, to the rectangular plot, there is a 6 dB drop or 6 dB difference. So basically, if we say that why are we getting the half and 1/4 of the amplitudes? So when we considered the rectangular window, so we had a full peak or full amplitude responding to the input. But when we are windowing the same thing, because we are waiting only for some sample in the middle and all other samples lying in this region and in this region. So for earlier we had a rectangular window like this. Over there all samples were considered, but now only this sample we are waiting for, and all other are getting weighted by a factor which is uh, basically less than 1 but not 1. So hence the contribution is lesser, basically, which is contributing lesser amplitude as well as lesser power. So if we see lesser power, so what do we mean by power? So power of the windowed sequence is basically uh, square of the amplitude. So it's 1/4 squared of half, and square root of 1/4. Basically, it is 1 by 16th and 1 by 16th. And when we add it together, so we get the power of our Hahn window. And basically the input power, if we take it as 1, which is given by a rectangular window. So basically the powers of the ratio of the powers is basically 3 by 8. So 3 by 8 came from this addition. So if input is lying onto the bin, then the input power is spread on 3 bins when we use Hahn window. And to find the true input power from the Hahn windowed FFT, we need to find the power in all 3 bins. So basically the power in all 3 bins, and then multiply it by the ratio 8 by 3, because the main input power was 1. So this is all about Hahn window. Then the thing we have to notice over here is when we use the uh, rectangular window of M samples, then we had a single peak, which is lying on, let's say if Fin was lying on the bin itself. So if it is lying on the bin, then there is no FFT leakage, and we are getting the peak amplitude as 1. So there is only one bin which is having a spike when we have a rectangular window. So this is our rectangular window, let's say. So when we talk about Hahn window, so if we had a rectangular window, we considered all the samples. But in Hahn window, we consider only some data which is in the middle, and the impulses or the spikes or the irregularities which were causing the FFT leakage, we tapered it out. So when we taper it out, so what happens in the coefficient domain or the discrete Fourier series, um, instead of one bin, it takes 3 bins now. But when we look at the leakage, so the leakage is causing because it is not periodic, right? So when we see uh, if there is if the input is lying on the bin, which is 129 sharp, then we have this graph. But we can analyze the leakage when the input is not lying on the bin, and when we analyze the situation, so the situation comes out to be like this. So this was the situation when we had the FFT leakage and all the bins are being occupied by the coefficients. But in the case of Hahn window, the FFT leakage is decreased by a significant amount. So this is what we were talking about, and this is the importance of getting a windowed sequence. So this is the benefit of using a Hahn window, because whenever we will have some kind of let's say FFT leakage, then the leakage will be reduced significantly when compared with the main case where we took only rectangular window. So there is one more window. So there are different types of windows. So apart from Hahn window, we also have a window which is Blackman-Harris window. So what happens in Blackman-Harris window? So it is a window where the discrete Fourier coefficients occupies more than 3 bins. Usually they occupy 9 bins when plotted against the log. So basically when we plot it throughout the bins in the logarithmic scale, so it occupies more number of bins. But as we saw, so as we saw in the case of Hahn window, we windowed the signal. So it occupied 3 bins. So now it is occupying more bins. But then when we talk about the FFT leakage, so let's take the case of FFT leakage. So when we talk about the FFT leakage, then we can see that in Blackman-Harris windowed signal, the FFT is reduced even more significantly. So our target is to reduce the FFT leakage. So windowing using a Blackman Harris, it will we can see that it is occupying more bins, but at the same time it is also reducing the FFT leakage by a significant amount, more than the squared window and the Hahn window. So this is for the squared window, this is for Hahn window, and this is Blackman Harris window signal. So this is the importance of windowing a signal. So why do we actually window a signal? So basically, these windows will be helpful in the concept of noise shaping when we talk about the delta sigma modulator, where we have an input which is sinusoidal along with a high pass looking noise. So we have a sinusoidal input. Along with that, we have a noise which is high pass filtered noise in behavior. So let's say that we generate this noise for the sake of analyzing the noise. So we have let's say we have a sinusoidal input, and along with that we have a noise. We can generate a noise. So how can we generate a noise? So let's take a white noise and pass it through a high pass filter. So over here we will take a fifth order Butterworth high pass filter. So when the noise is shaped, so then when we plot it, so this is a high pass noise, and basically this is our sinusoidal. So these are the number of bins or number of samples we have taken, and over we are interested over the signal to noise ratio of let's say a bandwidth of omega naught. So if we say that if this is our sinusoidal, so we are taking a rectangular window over here initially, right? So anyway, if we have to plot the discrete Fourier series, we start with rectangular window and then we talk about Hahn window and Blackman window. So let's see why we actually need so if we see, this is the center axis, right? It's the axis of symmetry. So let's talk about this half. So we have our sinusoid over here using a rectangular window, let's say. So we have a single peak of the coefficient, which is non-zero. And then we have our noise. So when we have a high pass noise over here, so ideally high pass noise, so high pass filter is basically, let's say this is its 3 dB bandwidth of this filter. So before, like after 3 dB, it will not provide any attenuation for the noise, but before 3 dB, or let's say for lower frequencies, it will provide higher and higher attenuation. That's what a high pass filter means, right? So ideally, when it approaches to zero, it should go to zero at infinity. So at infinity, it should provide in like at zero, it should provide infinite attenuation. But over here, we can see that again, there is some kind of FFT leakage. So why is it happening? So let's say, let's take a blank page over here, or maybe, yeah. So again, we have this length of a sample and we have noise like this, let's say like this. So this is the sample which will repeat itself again. So this is noise. Again, it will start from like this and go like this. This is another period. So this spike, again, we have a spike, right? When we take a discrete Fourier series. So we have a spike, and due to this spike in noise, again we have leakage, fast Fourier transform leakage. So due to the FFT leakage, instead of going to zero, or like at zero, it has infinite attenuation for a high pass filter, right? But due to the FFT leakage, we can see that it is planing out. So ideally, we were expecting behavior of noise like this. So it should go to zero at zero. So it should have infinite attenuation at zero. This is a high pass filter, but it goes somewhere like this due to FFT leakage. So to analyze this signal to noise ratio, we need a window. So if we are interested for this bandwidth omega naught, so if we window this signal using a Hahn window, or let's say using a Blackman Harris window, so then we can have minimalistic reduction in FFT leakage so that it will give a behavior of a high pass filter. So that's the reason we are using this windows. So in the next video, we will actually see that why we use this, how we use this FFT window to get a behavioral of a high pass. So that's all for this video. Uh, uh, Thank you from my side. So if you have doubts, do ask.